With our 10 decimal digits, we can represent any integer that we like. If we had the integer, for example, say 123, we can interpret this as meaning the 3 is in our ones place, the 2 is in our tens, and the 1 is in the hundreds place. Another way to look at that, we could say that this is 3 times 1, or 10 to the power of 0. Anything to the power of 0 is 1, so this is our 3's. The 2 is in the 10, so that means 2 times 10 to the power of 1. And our 1, so if I do plus 1, that's by 10 to the 2, or 100. And of course, if we solve this arithmetic, we get the number 123. We can do the same thing with binary. Now in binary, of course, we only have 0 and 1. Binary means 2, means we have 2 digits. But we can represent numbers in a very similar way. In the same way that when we get to 9 in decimal, we need to add an extra digit, after we get to 1 in binary, we need to add an extra digit and we'll go to 1, 0. 1, 0 in binary is 2. And then we continue to count from there. So 1, 1 is 3. Again, we've run out of digits, so we simply add another one. And we end up with a 3-digit binary number. 1, 0, 0 is 4. If we follow the pattern on, we end up with 1, 0, 1 is 5, 1, 1, 0 is 6, and 1, 1, 1 is 7. And we keep going. Every time we run out, we add an extra digit. Note that in our ones place, so if we look at our ones, so the rightmost column here, or the least significant binary digit, least significant bit, this column here represents how many ones there are. The next column over represents how many 2's there are. Notice that 1, 0 is the number 2. The next column over is the 4's, so 1, 0, 0 is 4 because this is the 4's column. So in the same way that we had powers of 10 down here, we now have powers of 2. We have in our first column 2 to the power of 0, which is 1. In the second column, we have 2 to the power of 1, which is 2. 2 to the power of 2 is 4. And 2 to the power of 3 is 8. So we can follow this same method to understand our binary numbers. If we wanted to represent, for example, the number 123 in binary, that would be 1111011. And if we look here, so if we look at the various places, so if we look at the least significant digit here, that again is 1. So we have a 1, or in other words, 2 to the power of 0. Then we have a 1 in the 2's place, or 2 to the power of 1. We have a 0 in the 2 to the power of 2 place, so I'll skip that. Then in our 2 to the power of 3, we have 1. 2 to the power of 4. 2 to the power of 5. And 2 to the power of 6. And if we solve for this equation, we will in fact get 123. So we have all of our binary numbers here, and we can see that we can indeed represent all of these numbers. In fact, I'll just, for completeness, I'll put 1001 here, which is 9. But how did I know that this number here in binary was the same as 123? How can I find the binary number given a decimal number? The way that we do that, so for example, let's start with our 123 again. If we consider the binary implementation of this, every time we divide by 2, in the same way as with a decimal number, if we divide by 10, what we are doing is we are dropping off the least significant digit. So if we divide by 2 here, or we can also consider that to be a right shift of 1 bit, we are dropping off the least significant bit. So if we take the remainder after a division of 2, we will find this bit here, and we'll be left with the number here divided by 2. And then if we repeat that again, we'll get the next digit and so on. So if we look at 123 and divide that by 2, that is going to be 61. and there is a remainder of 1. If we then divide the 61 by 2, we again get a remainder of 1. Now this first one up here was our least significant bit, that's this one down here. And now this second one here is our second least significant bit. That means that the number we have here, which is 30, is actually 11110. So when we divide by 2 again, it's the 0 that will drop off. And we can see that because it's 30, it's an even number. When we divide by 2, it is not going to have a remainder. So we'll end up with 15 and 0 remainder. So if we carry on in this process, we take our last result, divide by 2, and have a look to see if we get a remainder, we will get our binary number. And if we look here, we'll see that the sequence here, 1, 1, 1, 1, 0, 1, 1, is the same as the sequence that we had down here, which we've already confirmed is indeed 123. So this is how we can find the number. It's also worth noting that if I continue on, 0 divided by 2 is of course 0 with no remainder. And we can continue on like that. And that's the same as if we added preceding zeros out the front of our number here. It makes no difference to the value of that number. So this is how a computer represents numbers. A 1 would typically be a higher voltage, for example 5 volts, and a 0 would typically be a ground voltage. And so here, if we had 7, I think we've got 7, yep, so if we had 7 lines here, or including the 0, 8, if we had 8 wires and each wire had a different voltage, if it had a higher voltage, say 5 volts, 0 volts, and so on, then that would be a way that we can represent the number inside of the computer. In the next video, we're going to have a look at how we can add these binary numbers together, and we'll build an adder that works in the same way that a computer's adder works.